Hi all, and welcome back to Math 150. For today's class or today's lesson, you are going to need to print out the probability worksheet that I posted on Blackboard, and you're going to need a calculator too. So what I wanted to start with today was a quick review of probability and sample space, and then we're going to get into the additive rule and the multiplicative rules of probability. So as a review, we talked about in class that probabilities have to be values between 0 and 1. So it's always going to be a number or value between 0 and 1. If you know the probability of an event occurring is 1, that means that there is a 100% chance that it's going to occur. So it will occur. So if I said the probability it's going to rain today is 1, that means you have to bring your umbrella. If the probability of an event occurring is 0, that means it's not going to occur. If I said that means the probability that someone will pass the test is 0%, that means they're not going to pass the test. So we know that probabilities are values between 0 and 1. Probability of an event occurring 1 means there's a 100% chance it's going to happen. And again, the probability of an event equals 0 means it's not going to happen. And then we also talked about this idea that we can express probabilities as percents, decimals, or fractions. So for example, if I said the probability of an event occurring is 0.18, that is the same thing as saying the probability of an event occurring is 18%. And that's also the same thing as saying the probability of an event occurring is 18 over 100. Remember, percent means out of 100. And we can reduce 18 over 100. We can divide them both by 2, and we get 9 over 50. So the three of these are all equivalent. 0.18, 18%, and 9 over 50. Okay, so let's go back and talk about this idea of sample space. Well, we talked about this idea that the sample space of an event occurring is the list of all simple events or outcomes of an event happening. So we talked about it's a list of all possibilities. So if you flip a coin, you can get heads or tails. If you flip a coin twice, you can get heads as one possible outcome. That's a simple event. You can get heads, tails. You can get tails, heads, and you can get tails, tails. So there were 4 possible outcomes for flipping a coin twice. Let's take a look at this example, which talks about what happens if you roll a fair die. So you guys know that a die is a number cube. It's a cube with little holes in it, and the holes in it go from 1 to 6. So we have, I get to draw a little picture here, right? So here's an example of a number cube. There's a 1, here's a 2, maybe this guy has a 4 on it. Anyway, cubes have 6 faces, so it has either 1 dot on it, 2 dot, 3 dot, 4 dot, 5 dot, or 6 dot. So when we talk about rolling a fair die, the sample space or the outcome or what shows up on the top, like this guy over here. So we can roll a 1, we can roll a 2, we can roll a 3, we can roll a 4. Standard black. We can roll a 4, we can roll a 5, or we can roll a 6. And those are the possibilities for the sample space. These are all the simple events or the simple outcomes that we can get if we roll a die one time. So this is a sample space: 1, 2, 3, 4, 5, and 6. Well, let's take a look at the next question, which says, okay, let's find the indicated probabilities based on the sample space above. Okay, so let's find the probability that when we're on a die, we roll a 2 or smaller. So first of all, you should know that we have a denominator of 6 because we have a possibility of 6 outcomes. So I'm going to put 6 in the denominator. And let's find the probability we roll a 2 or smaller. So the probability we roll a 2 or smaller, well, that means the following. I could either roll a 2, and numbers that are smaller than that is 1. So out of these 6 options over here, we have 2 possibilities. I could either roll a 1 or a 2. So that means the indicated probability here is 2 over 6. We can reduce that to 1/3. And let's convert this to a decimal. So you're going to get on your calculator, and you're going to type into your calculator 1 divided by 3. And as a decimal, we get it's approximately equal to, rounded to 2 decimal places, 0.33. Or if you think about it in terms of a percent, that's equivalent to saying about 33%. So we have a 33% chance of rolling a 2 or a smaller on a fair die. Okay, so let's take a look at part B. what's the probability that you roll an odd number? Let's go back up here. Oops, let's go back up here to the sample space that we had. And let's talk about the probability that we roll an odd number. Well, the probability that we roll an odd number, taking a look at this sample space over here, that means we could roll a 1, a 3, or a 5, or the faces that could show up here would be a 1, a 3, or a 5. So again, out of those 6 possibilities, 3 of them would be odd. 3 6 reduces to 1/2. And 1/2 as a decimal is 0.5. And 0.5 as a percent, remember you pick up the decimal, move it 2 places to the right, is 50%. So we have a 50% chance of rolling an odd number because half of the numbers or half of the faces of these die are odd. Pretty cool, huh? All right, so let's take a look at one more example. And this last example here says, let's find the indicated probability that we roll a 2 or larger. Again, we have a possibility of 6. We have a sample space of 6. So I'm going to leave it as my denominator. The probability that we roll a 2 or larger means that we could roll, keep it at yellow, means that we could roll a 2, or larger means 3, 4, 5, or 6. So we have these 5 possibilities out of 6. So we have a 5 out of 6, 5 out of 6, and again, I'm going to get on my calculator and do 5 divided by 6 as a decimal. That's equivalent to saying 0.833. And the 3's repeat, so you put a little bar over top to represent that, which is equivalent to saying about 83% chance of happening. So there's a fairly large percent, there's a fairly large probability that we're going to roll a number on a die that's 2 or larger. So this is the sample space for, when we're looking at this is a sample space for 1 die, but I wanted to take a look at a more interesting example, which is let's list the sample space for rolling 2 die. So what that means, and I already have it listed here for you, but I want to make sure that you understand exactly what this chart means over here. Let's take a look at this example. So take a look here, and we have these ordered pairs. We have 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. So what we're going to do is we're going to call all of the guys, so you guys remember the coordinate plane, this XY, we're going to call all of the guys in the first value over here. So this 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6, all those guys for the first coordinate. That's going to be let's call the first one the red die, and then the second one is going to be the blue die. Right. So really what we're doing here is we're differentiating between the 2 die. We could also, between the 2 die, you could also call it the first die and the second die. So we could roll a 1 in the first and a 1 in the second. We can roll a 1 in the first and a 2 in the second. We can roll a 1 in the first and a 3 in the second, a 1 in the first and the 4 in the second, a 1 in the red and a 5 in the blue, a 1 in the 6 and a 1 in the red and a 6 in the blue, and so on and so forth. So we have this total list of possibilities here. And if you count them up, we have 1 2 3 4 5 6 times 1 2 3 4 5 6. So we have a total of 6 times 6, which equals 36 possibilities for outcomes if we roll 2 die. Now it makes sense we would have 36 possibilities because we have 6 possibilities for the first die, or the red one, and then we have 6 possibilities for the second die, or the blue one. So here's the sample space for if we roll 2 die. Well, let's ask some questions. So let's follow this up with some questions down here. Let's take a look at this example, which says, find the indicated probabilities. Find the probability that the sum of the faces you roll is exactly 5. Well, what does that mean? The sum of the faces we roll is exactly 5. Let's take a look at the faces here. If we were to add together these two, we would get 2. Okay, here we would get 3, so that's no. Here we would get 4, so that's no. Look at that. If we were to add these two together, 4 plus 1 gives us 5. So we know that one way that we can roll the sum of the faces of a die to give us a 5 is the first one's 4, the first one's 1, and the second one's 4. Well, if that's true, then you can kind of see that this would be true as well. So what if the first one's 4 and the second one is 1? When we roll them together, we also get 5. Okay, are there any other possibilities for when we roll them together, the sum of the faces would give us 5? I'm going to let you guys think about it for a second. There we go. 2 3 and 3 2. So if you sum these up, if you take a look at how many we have, Well, we know our denominator is going to be 36, right? Because we have a possibility of 36 outcomes or 36 simple events. And when you add together these guys over here, we have 4 out of 36. Well, 4 out of 36 is a fraction. If we take 4 and we divide it by 36 as a decimal, that gives us 0.11, rounded to 2 decimal places. And then as a percent, that's the same thing as saying 11%. Well, let's take a look at this next example. The sum of the faces that you roll is 7 or larger. So we're asking a bit of a different question here. For this one, we want to find the probability the sum of the faces we roll is 7 or larger. So that means the sum of the faces we can roll are 7, 8, 9, 10, 11, 12. And I want to make sure why it's not possible, why you understand that it's not possible for us to roll a 13. Remember that the largest value that we're going to get on each one of the faces are 6. And so 6 plus 6 gives us 12. So we're maxing out there at 12. So let's take a look. And again, it's going to be out of 36. Let's see if we can find the sum of the faces that we roll is 7 or larger. Let's take a look and let's break this down into smaller events. Let's try 7 first. So let me erase these guys here. Okay, let's take a look at all of the possibilities where we have the sum of the faces is equal to 7. Well, all right, so 5 and 1, that's not it. 4 and 2, that's not it. This is 6. So let's try something else. 6 and 1. Well, 6 and 1 will give us 7. What else? 5 and 2 will give us 7. And you should see a pattern here. 4 and 3 will give us 7. 3 and 4 will give us 7. 2 and 5 will give us 7. 1 and 6 will give us 7. So the probability that we roll exactly a 7 is 5, 1, 2, 3, 4, 5, 6 is 6 out of 36 for these 6 values here. So that's for 7, but is it 7 or larger? So now let's check 8. Let's do 8 in another color. Okay, so for 8, we have 6 and 2. 6 plus 2 gives us 8. We have 5 and 3. 5 plus 3 is 8. 4 plus 4 is 8. 3 plus 5 is 8. And 2 plus 6 is 8. Great. So we have 1, 2, 3, 4, 5. 5 elements in our sample space will give us the sum of 8. Okay, so we have 7, we have 8. Let's check on 9. And again, see if you can figure out the pattern that's going on here. Well, look at this. Look at this next diagonal here. 6 plus 3 is 9. 5 plus 4 is 9. 4 plus 5 is 9. And 3 plus 6 is 9. So 4 out of those 36 will give us 9. Let's make a beautiful rainbow here. Let's do 10. We have 10. 4 plus 6, 5 plus 5, 6 plus 4. 11. 6, 5, 5, and 6. And then 12. 6 and 6. So if we count up how many of these guys we have all together, well, we have 1, 2, 3, 4, 5, 6. 6 plus 5 gives us 11. 11 plus 4 gives us 15. 15 plus 3 gives us 18, 19, 20, 21. So 21 out of 36 and let's express that as a decimal. 21 out of 36 of those elements gives us 0.58. So there's a pretty decent chance that that's going to happen. Okay, let's take a look at the next example. Find the probability that you roll the same number on each die. All right, so the same number on each die means that both my red die and my green die have to have the same number on them. So let's check and see if we can find that. Hold on, let me erase these guys here. Oh, well, here's an example. Here's actually 2 examples here of where we have the same number on each die, right? We have 6, 6, and we have 5, 5. Let's see if there's any other ones. Here's 1, 4, 4, 3, 3, 2, 2, and 1, 1. So out of those 36 options, 6 of them are going to give us the same outcome on each die. So we'll call that 6 out of 36. And if we simplify that, 6 out of 36, that gives us 0.16, 0.17, rounded to 2 decimal places, sorry. Okay, and then for the last example here, let's find the probability the sum of the faces that you roll is less than 3. So that means you're either rolling a 2 or a 1. But I hope you see that it's not possible for us to roll a 1 because the smallest possible value we can get in the sum of the faces, sorry, I'm checking to make sure the directions were correct. The smallest value you can get in the sum of the faces is 2. And there's only one of those, and that's here at 1, 1. So to answer this one, the sum of the faces that you roll is less than 3. We only have one of them, and that's 2, and that's 1 out of 36. And as a decimal, 1 divided by 36, I'm going to check on my calculator, we get 0.03. So there's a fairly small chance that that's going to happen. Okay, so let's move on to another example. All right, so the following chart represents the favorite food from a group of 102 people who all belong to a local soccer league. So what we did is we asked a bunch of kids and a bunch of adults what their favorite food was, and it was a toss-up between pizza, pasta, and sushi. And so here, this 17 represents that 17 kids chose pizza as their favorite food. This 23 means that 23 kids chose pasta. This 8 means 8 kids chose sushi. And then on the row underneath, we have adults and their favorites. All right, so let's take a look at this. Let's find the probability a randomly selected person selects pizza as their favorite food. Well, because we're doing people, we have a total of 102 people. So our denominator is going to be 102. And the numerator says find the probability randomly selected person selects pizza. So that means this 17 plus 5, these people liked pizza is the best. So that's the same thing as saying 22 out of 102. And 22 divided by 102 gives us a 0.22 rounded to 2 decimal places. Let's try the next one. Find the probability a randomly selected person selects sushi as their favorite food. Again, we're doing this out of 102 because it's a randomly selected person, and there are 102 people here altogether. So sushi, we have these 8 kids and these 30 adults. So we have a total of 38. 38 divided by 102, that gives us 37, 0.37 or 37%. Okay, so for the next example, find the probability a randomly selected adult selects sushi as their favorite food. So for this, the denominator is changing a little bit, right? Because the denominator is saying find the probability a randomly selected adult. So now our sample space, or the denominator, is just going to consist of these groups down here, just the adults. So when we sum them together, we have 30 plus 19 plus 5. We have a total of 54. And out of those 54 adults, the probability that they selected sushi, and again, we're just looking at adults, that's 30 out of 54. So adults really like sushi. 30 out of 54. Again, I'm going to type this into my calculator, and I get 0.56 rounded to 2 decimal places. The next one, find the probability a randomly selected child selected sushi as their favorite food. So again, now our denominator is going to change because I'm not looking at all the people, I'm just looking at the children. So if we look at the children row here, we have 17 plus 23 plus 8. Well, that's going to give us a total of 48. And find the probability they selected sushi. Well, kids don't like sushi as much as other stuff, so we have 8 out of 48, which is approximately equal to 0.17. Rounded, again, we're rounding these to 2 decimal places unless otherwise noted. For the last one, find the probability a randomly selected person selected pasta as their favorite food. So let's go over here. So again, our denominator is going to go back to 102 because we're dealing with a randomly selected person and not just a kid. Find the probability a randomly selected person selected pasta as their favorite food. So 23 plus 19. That gives us 42 out of 102. And let's see, that is approximately equal to 0.41. Okay, so for this one, I just want you to be careful with your denominator and make sure that you know what the part is and what the whole is. But let's do one more kind of interesting example, which is what I like to call the pregnancy test example. And then we're gonna pause the video and I'm gonna post a new one that talks about the additive rule of probabilities and then the multiplicative rule of probabilities. But let's get through this one first. Let's take a look at this one for pregnancy test results. So here we have, excuse me, here we have a grid of pregnancy test results. And here, this grid breaks it up into true positives, true negatives, false positives, and false negatives. So let's talk about what a true positive is. A true positive means that 438 women took the test, the result came out positive, and it was correct. And a true negative means that 983 women took the test, they received a negative result, and it really was negative, so they weren't pregnant. Well, these are the more interesting cases, are the ones down here, are the false positive and the false negative. So this 17 as being a false positive means that these 17 women, they took the test, the result came out positive but was false, so they weren't really pregnant. A false positive means you got positive as your answer but it wasn't correct. And this false negative, this means that these 9 women took the test, it came out negative, but it was incorrect. So if a negative test is incorrect, that means that they were really pregnant. But it's like two negatives give you a positive. So the false negative, again, means that the outcome was negative, but they were really pregnant. The outcome was negative, but it was a false negative, so they were really pregnant. All right, so the first question says, how many women took the test? So let's sum these up. We have 438 plus 983 plus 17 plus 9. Okay, so when we add those together, 438 plus 983 plus 17 plus 9, we get a total of 1,447 women that took the test. Okay, so let's take a look at this next example. What is the probability that a woman took the test and had a negative result? So, okay, so a woman took the test. So all of these 1,447 women took the test. So that's going to be our denominator. What is the probability that a woman took the test and had a negative result? So we're looking at this column over here. And when you add together 983 plus 9, we get a total of 992. So we have 992 out of 1,447. And that gives us 0.685, which if we round that to 2 decimal places, we get 0. Oops, sorry about that. We round that to 2 decimal places, we get 0.69. So we have 0.69. What is the probability that a woman had a false positive, and what does this mean? Okay, so what's the probability that a woman who took the test obviously had a false positive, and what does it mean? So, all right, again, 1,447 women took the test. So the probability a woman had a false positive, so here's 17 had a false positive. All right, so 17 divided by 1,447 gives us 0.011 or 0.01. So this information is telling us that about 1% of the women had a false positive, which means that the test came out positive, but they weren't really pregnant. So in that case, the test is incorrect. We have a false positive rate of 1%, where the results came out positive, but they weren't really pregnant. So let's take a look at the next one. What's the probability a woman took the test and was actually pregnant? Okay, so let's take a look at this one. What's the probability that a woman took the test and was actually pregnant? So let's go back up here. We know that we have a total of 1,447 women that took the test. The ones that were actually pregnant, well, this one was actually pregnant, right, because they had a true positive. So we have 438 over there. And are there any other of these grids or any other of these outcomes, excuse me, that are still pregnant? Well, the true negatives are not pregnant, right, because it's a negative result and it's a correct negative result. The false positives, well, the false positives, again, the result came out positive, but it was false, so it was incorrect, so we weren't really pregnant. Well, what about the false negatives? Their result was negative, so their result came out as being they're not pregnant, but it was a false negative, which means they really were. So those 9 people, these 9 over here, were actually pregnant. So we have a total of 438 plus 9, which gives us a total of 447. In regards to probability, rounded to 2 decimal places, 447 divided by 1447, we get 0.31. And let's take a look at the last example. What's the probability of the last example for this video? What's the probability a woman took the test and was not pregnant? Okay, so a woman took the test and was not pregnant. All right, so let's go back up here and let's look at the not pregnant ones. Who was not pregnant? Well, we know that these were pregnant, right? These 2 were pregnant, but let's make sure that you understand why these other guys are not pregnant. Well, the true negatives took the test, they had a negative result, and it was correct. So those guys are not pregnant. So that's 983. And remember, the false positives, their test came out as being positive, but it was incorrect, it was false. So we have 17 there. And that gives us a total of 1,000. So 1,000 of those guys were false negatives. 1,000 of those guys were not pregnant. And if you add these up, the probability that they were pregnant plus they weren't pregnant, it'll give you 100%. That's the entire sample space. So it makes sense if this is 447, this would be 1,000, because 1,447 minus 447 would tell you which was left over, what was left over, which is 1,000 over here. Similarly, that these 2 values over here should sum up to 100%, or something close because of rounding. So when we do the math, we have 1,000 divided by 1,447, and that gives us 0.69. Okay, so I'm going to pause the video here, and when we come back, we're going to talk about the additive rules of probability and the multiplicative rules of probability.